Work. This term has several meanings in everyday language, and in the natural science, it has been given very specific meanings.
I'm Francisco Cruz. Welcome to MenteQuímik, your new channel of tutorials to understand chemistry. Today, I want to talk with you about work and its meaning in science. I hope you enjoy.
Before, I must advise you that for a better understanding of this video, it's preferable to understand the concept on screen. Now, let's begin. Work is represented with a W by the word work, and it is equal to the product of the force by the distance and by the cosine of the angle that exists between the direction of the force and the direction that the point travels or the moving object. While work is done on the body, an energy transfer occurs to the body, so work can be said to be energy in motion. But what does this mean? Listen up. This concept derives from the notion of the effort that must be made to move objects. It is intuitive that the effort is related to the force that it exerts, but it's something else. For example, a box of 10 kilograms multiplied by the acceleration of gravity gives us a total of 98 Newton. So we would need to exert a force of 98 Newton in the opposite direction to lift it. No matter how high you lift it, it will continue to exert the same force, but the effort, or what we will now call the work, will increase as the distance increases. We must take into account that it is a scalar magnitude expressed in energy units, that is, in joules, according to the international system. We saw the work done by a person lifting an object, but what would be the work done from the ground to the object? The ground performs equal and opposite work to that exercised by the person on the object. So, if a person does a 250 joules work, the ground will be doing a minus 250 joules work at the same time. If we move an object from one place to another, the force to be exerted is always the same, the one necessary to overcome friction, but the effort is greater the further we take it. But what if there's an inclination? We would calculate the same way, only multiplying by the cosine of the angle at which the work is carried out. We can see the work in different ways. Work due to weight, rotation work, work on a surface, and electrical work, one of the most influential on physical chemistry. The electrical work, which we can call electrical energy, is the work that an electrical force performs to a charge that moves from point A to point B. By the power formula, we can solve and find the work formula. Now, I have a question for you. In which of this system is no work being carried out? A. A blender on. B. Boiling water in an uncovered pot. C. Ball rolling. D. Compression of a spring. Could you find the answer? If your answer is B, you choose the correct option. What happened with boiling water is that it is not an example of work, but of heat. Do you remember the term heat? It is defined as the transfer of energy from one system to another through the variation in temperature. But what would happen if there was energy transfer without variation in temperature? This is where the so-called thermodynamic work comes in. We have already given a definition of work in physics, but in physical chemistry, work itself is defined as a transfer of energy by the action of a force, and not by variation in temperature. This definition can be assigned the term of thermodynamic work, while the concept of work that we saw earlier is called mechanical work. To talk about thermodynamic work, we are going to rely on the first law of thermodynamics. The change in internal energy of a system is equal to the heat added to the system minus the work done by the system. There's something that we have to clarify here. The fact that there's heat in the system doesn't mean that the work is not carried out in it. We have the example of the hermetic pressure cookers, a closed system that doesn't allow the volume to expand outside its surface, increasing the pressure. What doesn't happen in the example of boiling water. The heat causes the water to become steam and expand freely through the environment, which would bring the pressure to zero. So the equation would give zero. This process is called free expansion, and remember, if there's free expansion, the work will be zero. Let's look at the following example. We define the system as a gas within the adiabatic cylinder and the piston. The environment is everything not represented in the illustration. The gas has a volume of 450 cubic centimeters. The gas is compressed while a force is applied to the containing surface through the piston, meaning it added pressure, and the initial and final volumes are defined by the mechanical stops indicated on the screen. The volume went from 450 cubic centimeters to 250 cubic centimeters. In this case, let's suppose the pressure is 5 Pascal. What will be the work done by the gas? The work done is minus 1000 joules. Work done by gas, expansion. When the air expanded, the molecule lost kinetic energy and does positive work on piston. Work done on gas, compression. When the air is compressed, the molecule gains kinetic energy and does negative work on piston. Now, let's do a little more complicated exercise. A heater is immersed in a 100 grams sample of liquid water at 100 degrees Celsius in an insulated container on a laboratory bench at 10 elevated to the 5th power Pascal pressure. In this process, 10% of the liquid is converted to gas under pressure already mentioned. To carry out the transformation, it needs to flow through the heater a current of 2 amp from a 12-volt battery for 10 elevated to the 3rd power seconds. Water densities liquid and gaseous under these conditions are respectively 0.997 and 0.590 kilograms per cubic meter. What was the thermodynamic work done by the system? And what was the electrical work done by the heater to transmit enough heat to the system to produce the thermodynamic work? What happens here is that the electrical work produced the thermodynamic work. In this exercise, we are going to calculate both. We start by showing the formula and the data. 1 Pascal equals to 1 Newton per square meter. So we will replace this unit for easier. We have the pressure, but we lack the final volume and the initial volume. We will first look for the initial volume. The exercise tells us that we have 100 grams of water or 0.1 kilograms and gives us the density of water, which is 0.997 kilograms per cubic meter. The problem tells us that 10% of the water became steam and 90% remained water. 10% of 100 grams is 10 grams or 0.01 kilograms and the 90% is 0.09 kilograms. We use the density formula. By adding both volumes, we will obtain the final volume. We subtract and multiply. We can deduce that the work carried out by the system is 1.17 kilojoules. Now, we are going to calculate the electrical work that produced this thermodynamic work. The energy transmitted by the electrical work is equal to the heat that is transmitted to the system. We only multiply the electrical voltage by the intensity of the current over time, which is equals to 24 kilojoules. We note that as the volume expanded, the thermodynamic work was positive, and that the electrical work is a lot greater than the thermodynamic work that it produced. I hope you liked this video and that you have learned about work, especially electrical and thermodynamic work, these two great topics of physical chemistry. See you soon.